All right, welcome back, everyone. So today it's my pleasure to welcome Dr. Liv Vage, who will be talking about graph neural nets and reinforcement learning for practical tracking at the LHC. Yeah, thank you, Liv.
Thank you very much. And yeah, thank you very much for having me. It's a pleasure to be able to give this talk. So what I'll talk about today is almost a little bit of a case study into particle tracking at the LHC. So that's something where we've been using it's called conventional algorithms, and we're looking to use machine learning. And I've been looking particularly into graph neural nets and eventually reinforcement learning for that. So I'll kind of have to give a little bit of background and context, I guess, on the LHC. And what particle tracking is, and then we'll talk a bit about graph neural nets, which I'll keep a little bit brief because it's my understanding that there's been a lot of seminars on GNNs in this group. And then I'll talk a bit about reinforcement learning, which I think is kind of making maybe a little bit of a comeback, but is, I would say, certainly less common. So to dive right in, I'm sorry if some of you are very familiar with the LHC. This bit is then going to be a bit boring, but it's one of these things that has to be done. So some of you might know the LHC is this huge collider in France and Switzerland, 27 kilometers, where we collide proton-protons. And there's 4 main experiments that measure results. So there's 4 different parts of the tunnel where the 2 beams are brought into collision. And from that, you get a lot of interesting stuff that enables us to study particles. And the reason we do this is because, as you might know, there's a lot of unsolved mysteries in physics. Some of the big ones is dark matter. We know it's there. We have no idea what it is. Same with gravity. All the other forces has a particle associated with them. We haven't found a particle for gravity. We also observe much more matter in the universe than we do antimatter, and we don't actually know why that is. Again, we have some ideas, but there's no proof. And then there's also something called the flavor puzzle, which is we see these we call them generations of particles. We see a lot of different fundamental particles. We can't really explain why there are the number they are and why they weigh what they do. For instance, one of them is much more heavy than the others. How does that happen? So that's some of the big mysteries that we are trying to solve. And the way we do that, one of the main ways we do is that we try to verify what we call the standard model. So the standard model is this little graph that you can see here. It is just a description of the fundamental particles that we have found and their properties. And there's a lot of math that describes their interactions and their probabilities of decaying into other stuff. And we try to verify our understanding of it. And with a lot of these things, if there is something new, sometimes you can just spot it by, for instance, how quickly a particle decays or something like that. So we try to make very, very precise measurements to look for anything that doesn't look right. And one of the things that we are very preoccupied with is the Higgs boson that you might have heard of, that was discovered in 2012. That's the particle that gives mass to most of the other particles. So that is very important, and how it binds to the other particles helps us verify our theories. And there's also some new physics there in its properties that we don't quite understand or we're not sure about. So that is one of the most important particles. We also look for new physics. We do that by looking both at the standard model, but also looking for specific things that we might think may or may not be true. One of the common things that we are looking for at the moment, which we have been looking for a while without finding any evidence, is supersymmetry, which is kind of this idea that there's a lot of the particles have partner particles. We haven't observed them, but it's one of these mathematically appealing ideas. But then again, so was string theory, and we haven't really been able to find anything there either. So there's a lot of interesting physics going on. We do it by colliding these beams of particles, as I said. what we would love to do is just collide one particle with one particle, but you need an extreme degree of precision to be able to do that. So we can't do that. What we do instead is that we collide bunches of particles. So we have these really fast bunches of particles that go around this 27-kilometer tunnel. And as you can kind of see in this figure here, we bring them to a collision point. So there's lots of magnets around the beamline that bends the particle paths and brings them to collision. So these collision points will happen at each of the 4 main experiments at CERN. And that produces something super, super messy, like you can see over here, because you have a lot of particles that will collide in those bunches at the same time. And how we then detect the particles is, as you can imagine, quite complex. This figure here describes one of the experiments, which is called CMS, but this sort of general structure is very common for similar experiments to CERN. The main idea is that our detectors are kind of layered like onions, and we try to stop different particles at different points in the detector. So in the very inner part of the detector, we can see charged particles. So this will typically be silicon, and charged particles will leave signals in the silicon. And then we typically have another detector, like an electromagnetic, we call it a colorimeter. And then we have a hadronic colorimeter. So both of these colorimeter, they're made of material that is meant to stop the particles. So one of the main things we don't want is for the particles to kind of go out of our detector with still having energy, and we can't stop them, because one of the key things we're looking for is missing energy. So if we can kind of track, okay, there was a collision and we know that energy is conserved in the collision, if we can track all the particles that belong to that collision, then we can calculate the total energy involved. If we see missing energy, that's one of the main signs for new physics. So for instance, we have neutrinos, and they can't really be detected in our detectors because they're so weakly interacting. So we know there's going to be neutrinos, but there could be other stuff as well that we can't detect. And if there's lots of missing energy, that would be one of the key signatures. So therefore, it's super important that we stop all the other normal particles and they don't escape from our detector. So these colorimeters are made of materials that really try and stop the particles. That gets really messy, but that's a whole different kind of side to it. Most of what I'll be talking about today is the silicon tracker, the innermost part of most of the detector, where all the charged particles will leave a trace. And one thing to note as well is that most of these experiments are surrounded by a very strong magnetic field. And that magnetic field bends the particles, and by the curvature of the bend and the direction of the bend, you can tell the charge and the mass of the particle. And that's what we use to identify the particles. So typically this whole thing, we call it kind of reconstruction, because we can see traces in the detector and we have to reconstruct the particle collision to figure out kind of what happened and which particles belong to which part. This all poses quite an enormous data challenge, which I think is quite well shown in this figure over here. So you can see kind of latency requirements. So by latency, I just mean how quickly do you have to process information versus the data rate. So how quickly are you getting your information? And you can see Google Cloud over here and Netflix over here. And you can see LHC, I'll explain these terms in a minute, but the LHC presents one of the bigger data challenges of our time, at least right now. You can see it's divided into two, and that's because we have to process the information so fast that we have to do it with what we call triggers. So we produce so much information, and the reason the information is so big is just because we have so many sensors. So there's a lot of collisions happening at once, and also there's so many sensors that is just a lot of data. We don't want to store all of it, because most of the time when we collide particles, we just see what we've already seen, and it's not really interesting. We don't want to or need to store it. So what we need to do is to figure out a way to kind of extract, this is an interesting, we call them event. So when I say event, I just mean a particular proton-proton collision. So we need to extract those interesting events and store them for later. And we usually do that in a trigger system. So a trigger system will look for interesting signatures. So for instance, if we say, okay, this was a very high momentum collision, therefore it's likely we get something like a Higgs boson, then we're gonna accept that event, and we're gonna pass it through the pipeline to eventually be stored. That often happens in 2 steps. So we sometimes call it the level 1 trigger and the high level trigger. It's just a tiered trigger system, so that one is very fast, accepts some events, and there's another trigger that looks for other things and reduces the data size further. So that's how most of the experiments handle that huge information. So we have very low latency readout directly on the detector. So some processing actually happens straight on the detector, which is quite interesting because it's quite a radioactive environment, and it's quite a challenging environment. And then we also have kind of service tunnels that is also down there in the tunnel that does some of the very quick processing. So a lot of the machine learning that we're looking to do would target, or at least that I'm looking to do, would target these trigger mechanisms. So we would want it to be very, very fast. So a lot of these algorithms we are thinking to put on either GPUs, which is quite easy to do with machine learning these days, or also FPGAs, that is field programmable gate arrays. They're less common. They're a lot more difficult to program. It takes more time. Can also be a bit challenging for machine learning, but we have some in-house tools to help with that. FPGAs basically give you a more bespoke, it isn't a bespoke chip, but it's a reprogrammable chip that can have potentially a lot lower latency than GPUs if you use it right. So some of the machine, I won't be talking in detail about these co-processor applications, but I will be talking a little bit about latency because that is something that is quite important in these experiments. And again, one of the reasons is the data size is big, and also particles collide at CERN every 25 nanoseconds. So you need to be able to kind of buffer in the events and process them quickly enough. Otherwise, you're just going to overflow and lose information. So it's an interesting data challenge. The experiment I work on is called the CMS experiment. That's short for compact muon solenoid. It weighs about 14,000 tons. And I know you're wondering how many elephants is that? And that is 2,000 elephants. It has a very strong magnetic field, so it can bend the particles. And this is just one of the 4 detectors. So you have CMS and Atlas. Those are the 2 main experiments, the general purpose experiments at CERN. So those were the 2 that co-announced the Higgs boson discovery. And then there's 2 others, LHCb and Alice, and they are more specific to kind of looking for something a bit more specific. So I won't really go into the detail of this experiment. Most of what I'll be talking about today is applicable to all kind of similar style experiments. So now I want to talk about tracking these particles and how we do it. Essentially what we have in these trackers, so the innermost part of the detector that is closest to the beam line where we collide the particles, is typically silicon sensor layers. So we layer it something like this. It is actually quite interesting because you'd think initially we'd want as much detector as possible and as much granularity as possible, but we also want to keep the material as little as possible, because if we have too much material, then there's going to be a lot of interactions that we don't want, like stuff that is going to scatter the particles or stop them and just make the physics a lot more complicated. So we want to detect while also not interfering too much with the particles at that point. So that's why we have them in these kind of layers. And then when a particle comes through, typically it leaves these what we call hits in the detector. So what we will get as a readout will be positions of these hits. And then we have to kind of draw the line. So that's basically what particle tracking is kind of drawing this line and saying, okay, these hits came from the same particle. And from that, we can kind of create a function that describes the path of the particle. I think this is best explained with a little animation that I think you should still be able to see. Can you see this animation? Can you still see my screen?
Yeah. But we don't see
Fantastic.
Is anything moving or?
No, I stopped it, but you can see this gray screen, right?
Yes.
Fantastic, thank you. Good. So just a little animation to show this. So particles collide in the beamline. And then they go through here, other particles, they kind of create secondary particles that go through the detector and they leave hits. Now, we don't know which hits belong to which particles. So what we get as a readout will just be something like this, and it will be up to us to kind of figure out which hits belong to the same particles. So the classical method of doing this is to use a Kalman filter. So I'll talk a bit more about that, but a Kalman filter is just, it's a method that was actually originally used with kind of tracking rockets and stuff like that. It's very good when you have an uncertain environment. So you typically try to predict, if you, for instance, try to, you have a hit over here and you try to predict where is the next hit going to be. Then we have some, as you can imagine, we have some equations on how to kind of propagate a track. So usually you start with what we call a seed. We have some algorithms to kind of estimate the momentum of a track based on just a few hits. And then based on that, we try to propagate the track further and say, okay, I have these hit parameters, where is it going to go next? And then, as you can see by kind of these squares, there is an uncertainty associated with that. And you look for hits that kind of coincide with that uncertainty. So in this example, you could, for instance, say, okay, this is kind of the window where I'm going to look for hits. There's only one hit, so that's the correct one probably. And then you continue like that. If you have several hits compatible, so if you have several hits in the same window that it could be, then what we do is that we do actually have to consider both of those hits as a valid option. And then we have to propagate the same tracks through a lot of different possibilities. And that is basically because there's no way a priori for us to say this is the correct hit and this isn't. That can be very, very tricky. So what actually happens is that we split it into different candidates. So it's a very iterative process. Now, CERN, as I'll talk a little bit more about, is set to undergo a large amount of updates, and I'll explain this a bit further. But one of the main things that will come out of that is that there's going to be a lot more particles colliding at the same time. So there's going to be a lot more hits in the detector. One thing we are looking to kind of help the combinatorics that we would otherwise encounter in the Kalman filter, which I'll come back to more in a second. One thing we are looking to do is to create graph neural nets, which would look something like this, where you create edges between adjacent hits in the detector. So that is one of the concepts we're going to be talking more about. So let me just jump back to the slides. So just kind of to show again how the traditional tracking is done. If you imagine we have some hits and kind of these windows I was describing of kind of compatible hits are shown in blue here. You can see an example when you have several compatible hits in a window, you need to consider all the different probabilities and possibilities and propagate each possibility. And in this example, as you can see here, we start with one track candidate, as we call them, but it quickly splits into several track candidates. Now, the issue here is that we are upgrading CERN in many different ways. One of the main ways is that we're colliding more particles at once. Usually, per collision, there's only one kind of high energy hard scatter, as we call it, so kind of like a head-on collision between two particles that creates lots of interesting stuff. Some of the other ones, some of the other particles in that same bunch will kind of just graze each other or scatter softly with little energy. That creates what we call pileup. Is a lot of tracks that aren't really interesting to us because there'll be low energy, there'll be physics that is very, very well known. Is usually the high energy stuff that gives us interesting stuff that we don't know as well. So here is an example. The LHC right now is working with a pileup of around 50. So pileup just means the number of simultaneous proton-proton collisions. Right now, that's around 50. That's going to go to 140 and eventually 200. So as you can see here, this is kind of a visualization of what the tracks look like in those scenarios. And as you can see, you know, you have more stuff colliding, it creates other particles and then other particles, and suddenly you're dealing with a lot of tracks. And kind of coming back to these hits that we have in the detector, there's so many more hits, they're closer together. And when you have to consider lots of different possibilities for each track candidate, it becomes a massive combinatorial problem. So it becomes quite difficult to solve analytically. We have seen that we can do it. So given enough time and computing resource, you can absolutely do it, but you have to consider a lot of different candidates. You have to score all the candidates and then remove the fake tracks that you created. Like in this case, some of the tracks, like the one that is far to the left here, it starts out looking good and then it doesn't go anywhere, it doesn't find any other compatible hits, so that would be a fake track. So you have to come back and get rid of it. So that takes a long time and it's very challenging when we're working in low latency environments. And also, just for fun, the data volume, just because it's so big, the data volume increases by around a factor of 10. And we've seen with our triggers that if we kept the computing structure the same, then we'd need around 20 times as many CPUs, something like that. And that is very expensive and doesn't seem like a very good solution. And that's why we're thinking about machine learning. So tracking is one of the most time-consuming parts that we do in these triggers, and machine learning could be potentially a good solution here. Instead of always trying to consider all the different possibilities at each stage, we could learn from experience, we could learn from our data and try to eliminate some of that combinatorics. A very nice thing about these experiments as well is that we have to understand our detectors really, really well. And to do that, we have extremely accurate simulators of the experiments. So for instance, with some of the detectors that I showed a picture of, we need to understand to a very high accuracy, like the material effects that we're going to have, and you know, stuff like what would it look like if we did see a Higgs boson. So we have extremely accurate and excellent simulators, and that means we actually do have labeled data we can train on, and we can, in theory, get as much of that as we want, which is quite a nice situation to be in with machine learning. So we can leverage that and try and use machine learning. And I should say as well, machine learning is used a lot already at CERN, is used a lot in analysis. Like, for instance, a lot of the papers that CERN comes out with these days uses machine learning extensively. And machine learning was actually also used in the announcement of the Higgs boson, but that was boosted decision trees. But it is used a lot, mainly to discriminate signal and background, because we have a lot of data, and to kind of pick out what is the signal. So like a Higgs boson and what is just background, so lots of other particles, we do use machine learning, but we haven't so far put it into the triggers because it is such a low latency, challenging environment. But it's a very active field of research. So one thing we were looking to do is to put this tracking algorithm into graph neural nets. Now, as I said, I won't go into massive details about graph neural nets because it sounds like a lot of you will be familiar with it. The main idea, as I'm sure you know, is that you have data that is represented as nodes and edges, and then the real power of them comes from how they aggregate information about a neighborhood, which can be very useful in something like tracking. So, so for tracking, what we envision is that these hits in the detector, they will act as nodes. So the nodes will just be hit positions. And then we create edges between the nodes, and we try to learn which are the fake and which are the real edges. Now, we only connect edges that could belong to the same track and are adjacent in our detector. So here is a figure of, to the top here, you see a figure of one of our silicon detectors. And we only would connect adjacent layers in the silicon detector. And then we try to build a graph from that. And from that, we try to learn which are the tracks in our detector that we saw. One of the very popular GNN structures that we've used is something called an interaction network. There's a link to it here if you want to read more about it. It was developed by Google DeepMind. It's quite popular in physics use cases because the base idea is that you have almost like a cause and an effect. You have an object and then something has an effect on an object. Essentially, it is just two different neural nets that are used sequentially. And at the end, what we do is just we score each edge and we only keep the edges that are above a certain threshold. So to visualize that a bit better, you can look at this figure here. So all of these gray dots will be hits that we had in the detector. And this figure is then made after we run the inference. So first we trained it, and then we run the inference. And you can see these true positive edges, for instance, here. You can see all of what our algorithm thinks was a true track. So all of these edges are built kind of one by one and then connected together. As you can see, we also have some true negatives and a few false positives and false negatives as well, as you will always have. You can see there's a lot more negatives in the middle here. And that is typically caused by just kind of where we have a lot of hits. So closer to the beamline, there'll be going to be a lot of hits because there's a lot of stuff coming out there. So there's just going to be a lot of hits. And we have to create a lot of fake edges that we can then classify as negative. And yeah, we're not going to worry too much about this graph. The main takeaway is that the edge classification accuracy is pretty good. It's pretty good at doing that. But there are some simplifications that have been used. So there's quite a few different simplifications. Some of this early work has removed a lot of the hits to simplify the problem. There are also a few limitations that I don't think are too interesting if you're not very into particle tracking. But one of the main important points is that these results are given with some simplifications, and also that one of the main challenges is that the graph building is really slow. It can be very, very slow. So this is kind of run on a CPU, but if you try to build a graph of one event and you use just a tiny part of the silicon detector, that can take up to a minute on it, if you just do it in one thread on a CPU. Obviously, you could speed that up by doing it on a GPU or just, writing the code better. But it's still to the point where it doesn't meet our latency requirements at all. And that is because of the number of fake edges that we build. Because there are so many hits in certain parts of the detector, we can't eliminate those edges early on, and we need machine learning. But obviously, you need to first build the graph before you can do any machine learning on it. As you can kind of see in some of these figures, there is just a very high number of edges compared to nodes. So we're just building a lots of fake edges. It's kind of shown in this purity metric. So sorry, I should say as well, this is done with essentially a different types of simplification. So further to the right in these figures are simplified more. So in a more realistic scenario, you'd have something like 1% of the edges that you build are actually true edges. So most of the edges that you build, which does take time because we also use information about each edge, are just fake edges. So we are spending a lot of time on building stuff that is just going to get thrown out. There are a few ideas to address this. One is that we use something called the module map, where we try to look at historically what parts of our detector have tracks that are connected. So we look at actually just silicon modules. So say that silicon module A usually has a hit in silicon module B if a track has a certain trajectory, and we create a mapping out of that, and we subset our graph based on that. Another idea is that we can try to embed all the hits into a learned embedding space. Both of these work fairly well, but they also take time. It's a time-consuming process. And so far, no one has managed to create something that is quick enough for what we need. Which brings us to reinforcement learning. So I should, I think, preface this by saying that this was something that I worked on during my PhD. It's not something that is particularly popular in the field of particle physics. I think it's kind of starting to gain some traction now, but all the work I'm going to present is just my own work. So it is, I'm very happy to admit it certainly has some flaws. But one of the things that drew me to reinforcement learning is kind of this idea that, you know, you have an agent acting in an environment. Reinforcement learning had maybe a little bit of a lull for a while, but I think with stuff like ChatGPT coming out, you can really see the power of it again. So you have, as you might know, you have an agent acting in an environment. Based on how it's acting, it's going to observe a reward. And then you just, it is quite similar to many other machine learning methods in that you just usually use gradient descent to try and update how it behaves to get a better reward. So there's lots of different types of reinforcement learning. You can see a little chart of it here. As is the case in machine learning with the no free lunch theorem, there's no way to know without testing which is the best method. You're going to have to try a few of them. One of the deciding factors when you're doing reinforcement learning is that you have to decide whether you're using a continuous or discrete action space. So that is basically, are you predicting a continuous number or are you predicting a discrete number? And that'll become clear later. But it usually takes a bit of trial and error. So if you're thinking, oh, my research or my data might be useful for reinforcement learning, here are some of the things that you might want to consider. One of the first things to think about is whether it fits the reinforcement learning criteria. So typically, you require the problem to be intractable and sequential. So because you have this idea of an agent acting in an environment, you see rewards based on the actions, that kind of has a natural sequence to it. That could mean many different things. It could mean, you know, a video game that, you know, you have an action, a consequence. It could mean a language model. You have an input and then someone gives you an output, or similar situations. You also need access to large data. Reinforcement learning, as I'll say a few times, is a bit more brittle, a fair bit more brittle than some other machine learning methods. And I would say as well, because it is less common, you'd have to usually be prepared to write more code from scratch as well, compared to, it's not there, as far as I know, there's no good kind of package where you can just use it out of the box like you can with sklearn or even PyTorch. So you'd have to do more manual labor. And that obviously also introduces a lot of potential for bugs as well. Most reinforcement learning also assumes that the environment is Markovian. So it does kind of assume that given that you have a certain state of the environment, that state is a full description of where the agent is going next. It's not a firm criteria. There are ways around it, but that's a general rule. And if you're looking to do something in RL, I think one of the best tips I can give is to start simple. Because compared to other methods, reinforcement learning can go wrong in many strange and unforeseen ways. For instance, the way you set your reward can be a bit non-intuitive. Like, as a very simple example, if you're trying to train a reinforcement learning agent to play chess, it could be tempting to, for instance, set the reward as, it gets reward if it captures a piece. But that's not actually the aim of the game. The aim of the game is to win. And while it's related, it isn't actually reflective of the game. So then you could get an agent that just learns to capture pieces, but never actually wins the game. So you need to really fine tune it. And one of the best ways to see patterns like that is to visualize the learning, so you can see where it's going wrong. Again, it might sound quite obvious, but very often it can be hard to see what it's actually picking up on in the data. So I'm just going to jump straight into how I used reinforcement learning for this project. So again, the idea that I wanted was to try to have an agent learn from the data, where is my track going to go next? So the GNNs, they were promising, but they were so slow, and we're spending so much time building these fake edges. Maybe an agent could just look at a hit and say, okay, based on all my previous experience, this is where it's going to go next. So that's what I tried to do. First, I tried with a continuous action space. So what I mean by that is just that I'm predicting continuous numbers. I'm literally predicting, based on this hit position, what is the next hit position. In reality, these tracks are three-dimensional. Actually, they usually move in kind of a helix, but that is quite a complicated motion to learn. And again, in thread with starting simple, I wanted to avoid that complicated helix motion. So instead, I made the problem two-dimensional, and that just means that the track should be a straight line. And I tried to get it to learn that. Here you can see an example where you have the true hits in black and the predicted hits in blue. And what we can see is that this is quite representative of what it learned. A lot of the time, it is, somewhat close to the mark, but also a lot of the time it is quite far off. And how it comes, it seems so simple, right? Especially this example is just a very nice little straight line. Why would it predict stuff that is further away? And again, that kind of comes with visualizing the machine learning, and you can kind of sometimes tell that because it's been given, some bad tracks or something like that, it picks up on weird patterns. So just to kind of delve further into how these algorithms work, I want to show you one of the very common ways to learn continuous spaces like this. So reinforcement learning, where you have an agent that wants to predict continuous numbers, like hit positions. So the most basic thing you can have is called a vanilla policy gradient. as kind of is given away by the name vanilla, there are lots of other algorithms that do similar things as well. This is one of the most basic ones. And it is actually very simple to other machine learning paradigms. You feed some observations in. Typically, that will be a description of the state. So in this example, it would be, what is the current hit position, for instance? Or even what was the current 2 hit positions, or something similar. Now, typically, which is a little bit different, we won't directly predict, let's say, the next hit position. Instead, it will predict parameters of distributions. So here, for instance, it could predict parameters of a Gaussian distribution. So that's kind of saying that for each possible input I could have, I have an associated Gaussian distribution. Now, the reason for this is because we want, usually, the reinforcement learning training to be probabilistic. So in reinforcement learning, which is quite unique to that subfield as well, there is a trade-off between exploration and exploitation. So you want your reinforcement learning agent to be able to explore a new area it hasn't seen before. But if it does too much exploring, it doesn't exploit what it has already learned. So there is a trade-off there, that it needs to exploit what it's learned, but not to stagnate. If it stops exploring, then it stops learning. And that's why we usually have these, something akin to this, where you sample actions from a probability distribution. Typically, as you train, those curves will kind of narrow. So let's say I have an observation. I say, okay, my hit is in this position. And then that neural net will give me some sort of Gaussian distribution. And I will sample my action from that distribution. So I will say, okay, based on that distribution, I'm going to sample my new, let's say, X and Y position. And then I update the state and say, okay, I did follow that. Now I'm in this position. What was my reward? Now in something like this, the reward is quite simple. It could simply be the distance between the correct hit and the predicted hit. And it sees the reward, and it will continue this iteratively, collect the rewards, and then it will update the policy. So by policy, we just mean something that determines how the agent will act. And it will continue this iteratively. And as it trains, typically these distributions, the distributions that we learn, will get more narrow as we get more certain about where it should go next. So that is a very common paradigm. A lot of other similar reinforcement learning methods that are in a continuous environment use something similar, but address specific theoretical shortcomings. So one thing that can happen is something we call catastrophic forgetting, which you can actually see in this figure here. So on the bottom here, I have a figure where you see I've trained a lot of different algorithms to try and learn how to predict the next hits in a track. And you can see this orange line here suddenly just drops to the bottom. So what has happened there is that it is done what we call a catastrophic update. So it has learned something, maybe from its explorations, and it turned out that was a really bad policy. It learned something that wasn't actually very usable. So then it forgets, and then it has to kind of relearn. So that can happen in reinforcement learning. You won't really see this sort of behavior with many other machine learning algorithms, which is one of the reasons why typically you have to try out different algorithms. And as you can see, some are more stable than others. Typically, the more stable ones often take longer to train, as you might imagine. Here's a little visualization of what it actually looks like if we try to predict different hit positions with reinforcement learning. So you have the true track going in red, and then you have the predictions coming in blue. So you see that some of them look fairly okay, and some of them don't look as good. The main takeaway that we had from this is that it can learn fairly well, to maybe within a centimeter or something like that. But that's not good enough for our needs. If we just look at it now, it seems like, okay, that's actually good enough. But if you look at how many hits we actually have at a time from one event, it is so many that if we just can predict within 1 centimeter, that will leave us, that won't exclude a lot of the hits. In each, I haven't showed them in this figure, but in that event, you'd have, let's say, 5 compatible hits at each stage. So it's not precise enough that we can use it. It could be usable, but I think a lot of more work would have to go into how to make it more precise. And one of the main things that made me go away from this approach is the fact that for each event, we get a reading of where the hits are, right? We kind of get an output that says, this is where in the detector your hits were. In this, I'm not really using that information well. I'm letting it predict anywhere in space it wants. And in fact, that's not true. I know that there are hits in certain positions. So I'm not making good use of the information I have at hand. I could probably do it better. I have tried to just kind of correct the hit position to where I see the closest hit, but that doesn't seem to help the learning. So another approach that I tried was to discretize the space. Now that is quite tricky. Our detectors are huge and extremely granular. We are down to micrometers in terms of granularity. So if we try to discretize it, it'd be huge and unmanageable. I didn't find anything in literature of someone trying to discretize a space like that. Typically, what people do when they're faced with a problem like that is do what we saw in the previous slide, that you try to use a continuous action space, you try to predict a continuous position, and then afterwards you correct it to a discrete space. Instead, I wanted to try something a bit different. So I want to emphasize this is quite, let's say, creative machine learning. I haven't found anything similar in the literature, so it's quite experimental. I tried 2 different methods, and I tried to kind of emphasize on I actually know where the hits in the event are. So if we consider 1 hit, our task is to predict where is the next hit, right? And my thought was maybe we can give it a little, let's say, selection pool of different hits it could be. I tried 1 method where it just sees 1 hit at a time, and it tries to learn the quality of that hit. So for each of the, I kind of repeat for each of the different hits, I try to learn a quality. So given the state, and given that this is your potential next hit, what's the quality of that hit? I also tried a different approach where it sees all the alternatives at the same time. So here it has the information that says, okay, you know, these are all your candidates. A problem here is that now we have a discretized space, right? So instead of predicting continuous numbers, what we do is that we try to learn a quality. So my action in this case would be the action that has the highest quality. Now, it's kind of a peculiar situation because let's say that I kind of, I have, in this case, I have 5 possible hits. So it would give me a quality for all of those 5 possible hits. What it would essentially, so it kind of, if I try to make it similar to what we might have in some known reinforcement learning problems, you typically have in a video game or something, you could have a discretized space where you have, for instance, you know, you can move up and down and left and right. That would be a very similar environment, but in that case, up and down and left and right always have the same effect. In this case, the hits move around in the detector a lot. So it could look like this, or you could have 5 compatible hits that are in a cluster over to the side, or they could be spread out. So kind of, let's say, action 1 might not always be going to, for instance, the left. It could mean going
I think we lost your sound, no? I can't hear you.
Try.
Oh yeah, now it's back. Yeah.
Okay, sorry about that. Thank you. Yeah, so in this case, there is no real association with the action and what happens in the environment. So taking action 0 could mean going to the right in one case and going to the left in another case. I couldn't find anything in the literature that had done something similar. So I thought this might break the learning because you have a very strong disconnect between your actions and the effect on the environment. But it turned out it seemed pretty good. And we got some interesting results with it. So in this case, it's given a number of hits at a time, and it tries to learn a quality for each of those hits. The best hit is chosen, and it updates the track. And it does so iteratively until the end of the track. Now, compared to the continuous environment, it's not just trying to predict the hit's position, it's actually given positions that I know are possible given the hits that we have available in that event. The major drawback is that this time we have to actually kind of find the compatible hits first. So we have to give it those, like in this case, we have to kind of pre-select these 5 hits to give it as a possibility. And that brings a kind of selecting those hits does take some computing, and that brings us back to something maybe a little bit similar to a Kalman filter. But we do reduce the combinatorics because we don't have to consider all of the different options and propagate the tracks in each of those directions. We can actually just decide this was the best hit and leave it at that. So we do reduce combinatorics, but it still does take some time. I also wanted to, similarly to what we did in continuous learning space, I also wanted to try and give us a bit of an intuition of how you learn something in a discretized space. This is called, one of the simpler paradigms is called Q learning, because you try to learn the quality of your different possible discrete actions. In a super simple scenario, you could have a table of qualities. Like this is a very traditional example. Like for instance, if you have, a taxi and you're trying to get it to learn to pick up and drop off passengers or something like that, then you could try out you could enumerate all the possibilities and assign qualities to each of those. That's typically not feasible because having a huge table like that and trying all the possibilities is typically not possible. So what you do instead is that usually there's 1 or 2 neural nets involved in the process. So instead you try to learn the quality of the different possibilities with the neural net, and that enables you to learn qualities without trying all the possibilities. You can find fun examples of kind of deep Q learning with, for instance, chess. There's very accessible examples there. Getting it to play good chess is obviously not as simple, but it will play some chess through stuff like that. So some of the methods I used this sort of idea. So as you can see here, it does kind of get to a fairly good accuracy. So this can loosely be translated to an accuracy. As one might expect, if I just give it 2 hits candidates, it's a lot easier for it to learn. So this was quite early work. There's a lot more to be done here. I think so far it has shown that it can help reduce the combinatorics, which could speed the problem up, but because there is still some time spent on hit selection, there is no proof yet that it would be faster. But it is an interesting direction, and reinforcement learning is quite new in the field. So I think if more people were working on this, I think it could take an interesting direction. So just a quick summary there. As we saw, the LHC is upgrading, and it already is, and even more so will be after the upgrade, a massive computing challenge. Huge amounts of data, low latency. Tracking is one of the more time-consuming things, especially that we do at the triggers. And the classical approaches work, but they seem quite slow. So we have tried GNNs is the most kind of, let's say, accepted method at the moment, showing promise, but hasn't shown the latency we need. Reinforcement learning, again, as I said, is only me working on it, so it's not quite comparable to where the work on the GNN is, because that is a larger group that has been working on it. But it is definitely showing some promise, and it has, whereas the GNN still has the combinatorial problem, you don't have that as much in the reinforcement learning. You don't have to spend a lot of time building the fake edges that you do in GNNs. So definitely some work to be done. We haven't kind of found one method that everyone agrees is the best yet, so we're still working on that. So yeah, that's all I had. Thank you very much for listening.
Thank you very much. Thank you. Any questions or comments? It seems no comment. So maybe just a question about the data, the massive amount of data. Are you aware like techniques for model reduction being used to reduce the amount of data? Because it just seems to be so much data that it seems like model reduction is the right thing to do, or trying to find structure or.
Yeah, exactly. So what we do is that at the detector level, there will be some data reduction. So some of the signals are not even read out because we say, okay, that signal wasn't high enough to be important. So that's the first step. And then after that, we have our triggers. And they have kind of complex algorithms that are very, very quick. Like for instance, our first level trigger, that is, I can't remember the latency in my head, but is rapid, and that will kind of try to, we can't throw away events that could be interesting, so we do have to do some reconstruction, like some of this tracking I was talking about. We do that kind of on the fly very quickly, and then after that comes another trigger that looks a bit at it more detailed. So you are right, we're not storing all this data, we're using the triggers to reduce it, and then it goes on further. Yeah, but even after that, there's still a lot of data.
Yeah, okay. Thank you.
Mm.
Yeah, someone asking you a question on the chat.
All right. Right, so yeah, the question on the chat there, can you give us a general idea of how much data do you face with? So I'm not sure if that was me personally or the experiments in general. If it is the experiments in general, then I think this figure is probably most representative, that you are facing kind of on the petabyte per second data range. To maybe put that into more a bit kind of related to the talk and kind of the tracks, what we would typically see, let's say in terms of a graph neural net, is that you could have 300,000 nodes, let's say, that all represent hits in an event. And then you have to connect the edges, and then we're talking, at least tens of millions of edges that you all have to classify. And since we have a low latency, typically you'd have to process that event in, let's say, 0.1 of a second. So you'd have to build that graph and then run the GNN of it in that time. And tracking is just one small part of the data that we have to process.
All right, thank you. Other questions or comments? All right, seems not. Yeah, thank you again, Liv, for the nice talk. And,
thank you very much.
Looking forward to see everyone during the next 2 weeks. Yeah, thank you. Bye-bye. Thanks.
Thanks.